All right, here in section 13.7, we're going to start looking at linear approximation now for multivariable functions. So here I have a surface with the equation z equals f of x, y. And let's say we're at this point with coordinates a, b, f of a, b. And we want to know something about the local behavior of our function near this point. Okay, well, just like we did with linear approximation in Calc 1, where we looked at tangent line approximations to curves, we're naturally now going to look at a tangent plane approximation to this surface, okay? And I'll still call this the linear approximation L, right? Just like we did in Calc 1. And I can write down a formula for this tangent plane as follows. Okay, z is equal to f of ab, which is just the z coordinate of our location right here, plus this is the partial derivative of our function f with respect to x evaluated at ab, so this is just a number, keep in mind, times the quantity x minus a, plus the y derivative of our function f evaluated at ab times this quantity y minus b. Now I'll derive this formula here in a few minutes, but I want to, for now, just highlight the fact that this is really similar to the formula we saw for the tangent line in Calc 1, right? There we had f of a plus f prime of a times x minus a. So it would, it's definitely at least believable that this tangent plane equation would look something like this, right? Because we now have both the x and the y slopes to contend with, so it makes sense that both of those expressions are showing up, okay? But again, we'll come back to the derivation here in a moment. Now, we can also refer to the tangent plane as the linear approximation to our function at the point AB. And you'll notice this is just the same formula as above, right? All we're really doing here is just highlighting the fact that this plane here in green is giving us a linear approximation to our blue surface, right? And this thing in its own right is a function of two variables. And so we'll call that thing L of xy here. Okay, so now let's go ahead and argue why the formula for the tangent plane looks as it does. And so here, the first thing to observe is that our tangent plane is a linear function, right? So it's going to look something like this. It's just going to have an x and a y in it in some regard, okay? The other thing we know is that the tangent plane is going to contain the point where we're located. So in other words, if I plug in a for x and b for y, I should get f of ab for the z value. And so notice, right, this form satisfies that condition. Because if I set x to a, this will go to 0. If I set y to b, then this will be 0. And then I'd get that z was f of ab. So that's good. The other thing to notice, right, is that if I differentiate z with respect to x, what am I going to get here? Well, the f of ab, that's just a number, right? And so that would have a derivative of 0. And from this part, I'm just going to get a, because the a is just multiplying the x, and y is held constant, so this whole thing would be 0. So this, in fact, is just a. But on the other hand, looking at this picture here, okay, we're asking, well, what's the slope of our plane as we move in the positive x direction? And since this thing is a tangent plane, right, that should be the same as the slope of our surface as we move in the positive x direction, right? That's really the same idea that we saw with linear approximation in Calc 1. The tangent line has the same slope as the curve at the point where you're located. Same idea here, except now I'm just thinking about the slope in the positive x direction. So put another way, we could say that, right, this slope of our plane in the positive x direction is the same as the slope of our surface in the positive x direction, and that's just, of course, the x derivative of our function evaluated at AB. All right, by a similar argument, del z del y, well, that's b. And that would then have to equal the slope of our surface in the positive y direction. And that's just our y derivative of f evaluated at AB. And then if I substitute these into here and here, I'm of course going to get this formula up top. So that's really all there is to it, okay? And the other thing, again, just to keep in mind, these things are just numerical values, okay? So this is just a linear function in x and y. All right, so now let's see this in action. So go ahead and pull up question 1 on our worksheet. It says, find the equation of the tangent plane to the surface z equals x squared plus y squared at the point 3, 4, 25. Okay, well, essentially all we really need to do here is compute some partial derivatives. So let's go ahead and do that. So what would fx be at any point? That would just be 2x, right? And so if I evaluate this x derivative at 3, 4, I'm just going to be doubling the 3, so that's going to give me 6. All right, not too bad. Let's do the y derivative. So the y derivative of our function at any point xy would be 2y. So then evaluating this at 3, 4 would be what? Well, 2 times 4 now, so that'd be 8. All right, so then for the tangent plane, at the point 3, 4, 25, this would be what? Well, it'd be z is equal to, and by the way, where's that 25 come from? Well, if I set x to 3 and y to 4, 3 squared plus 4 squared is 25. So that's where this comes from. And in our formula for the tangent plane, we just said, look, take the z coordinate of where we're located. In other words, the value of our function at 3, 4. So that's just 25. And then we're going to do plus the x derivative evaluated at 3, 4. So that'd just be 6 times x minus a, and a here would be 3. And then we're going to do plus the y derivative evaluated at a b, so in other words 3, 4. So that's just 8 times y minus 4. And that is it. All right. Now for part 2, right, this says find the linear approximation L of xy to the same function at the point 3, 4. So same function, same point. Really all this is just a change in terminology, right? L of xy is the tangent plane. So in fact, this thing is exactly the same as our answer to question 1. All right, so there's that. And then it says, approximate the function value f of 2.9, 4.2 with the linear approximation. Okay, so all we're asked to do here is to say, okay, I want to approximate this function value. And notice 2.9, 4.2, this is reasonably close to our base point of 3, 4. So our function value for f should be reasonably close to the function value for the linear approximation. Okay, so what I'm going to do here is just plug in 2.9 for x and 4.2 for y, and that's going to give us what? Well, 25 plus 6 times 2.9 minus 3, that's minus 0.1, and then plus 8 times 4.2 minus 4 is 0.2, okay? And when you do that, you get 26. All right, so we're saying that our function value is at least approximately equal to 26, okay? Now it turns out if you use a calculator and you just put in 2.9 squared plus 4.2 squared, okay, you're going to get 26.05, which of course is really, really close to our approximation of 26. Okay, now this really is just to illustrate the fact that, yeah, I mean, L is giving us a reasonably good approximation to this. You might wonder in today's day and age with computers, right, when would you actually want to use this kind of approximation? I mean, function values in principle can always be found. I can just put them into a machine. It might be a messy calculation, but it could be done, right? And the answer there is essentially, yeah, you can. Where linear approximation really becomes powerful is in solving differential equations, and in particular solving systems of differential equations. Because when you linearize, you then get all of the tools from linear algebra to start to come into play. And that's where this idea really, really starts to become powerful. Okay, so I wanted to just say that in passing. The last thing we're going to look at in this video here is just a little picture here to help us kind of visualize what we just did. Here's our surface, x squared plus y squared, so our nice circular paraboloid. And then here's our point, 3, 4, 25, which I got to zoom out here. So we're way up here, right? And we found that the equation of the tangent plane at this point was 25 plus 6 times the quantity x minus 3 plus 8 times the quantity y minus 4. So here I'll get a little side view there. That is our tangent plane, and you can see we come in and we just sort of kiss the surface at that one point there in red, right? So it's doing what we would expect. All right, great. Well, that's going to do it for this video. I'll see you for question 3 next.